Section 2.2, acceleration. We're going to have three objectives today. First, to describe motion where there's a change in velocity. Second, compare graphical representation of accelerated motion. And third, we're going to look at our kinematic equations. First, let's start with the definition. Acceleration. Acceleration can only occur when you have a change in velocity. So it's the rate at which velocity of an object changes over time, which is exactly how it's defined here. Again, acceleration is the change in velocity over the time period that is undergone. A lot of people think of it this way, which is fine because that's what delta means again. And the delta you can drop on the bottom now, because traditionally you're given a time period. You're given the delta t, so we simply write it as t there. Notice the units. The units of velocity up here are meters per second. The units of time are second. So we end up having meters per second divided by seconds. Okay, that's what this really says up here. Meters per second divided by seconds. So when you divide, remember to multiply by the reciprocal. So we can, instead of doing that, we can switch this. Write it as the following. And seconds are really over 1, so the reciprocal will be 1 over seconds, which is what gives us meters per second squared as our units for acceleration. The units will always be length per time unit squared. Again, some length like meters, centimeters, feet, over some time unit squared, like second squared, minute squared, hour squared, any of them. Alright, the first example says a shuttle bus slows down with an average acceleration of negative 1.8 meters per second squared. How long does it take the bus to slow from 9 meters per second to a complete stop? Alright, so right away we know the acceleration is given, and since it's slowing down, that's why it's negative. So the acceleration is negative 1.8 meters per second squared. It says that it's slowing down to a complete stop, so the final velocity has got to be 0. And it's slowing down from 9 meters per second to that stop. Now this problem says, how long does it take? How long does it take? Well, we have to think about what we know. We know acceleration, we know change in velocity, we know, and then we're looking for the time period. So let's start with our formula. But I want to get time by itself, so let's multiply by t and divide by a simultaneously to give us this. And then redefine delta v as... Some of you might be saying, but you know what, wait, then we're going to get 0 minus 9 up top. But the denominator is negative already because it's a negative acceleration. So the numerator's got to be negative because negative over negative would yield a positive there. So now what we have to do is just plug in numbers. Alright, so what we're going to end up getting here for a time period is exactly 5 seconds. It's going to be negative 9 over negative 1.8, which is 5 in the units of seconds. We know our units are seconds because we can do this. We can just realize that this part of the equation doesn't matter. We can cancel meters with meters. Seconds are one of those seconds, leaving seconds behind, but it's in the denominator of the denominator, which technically moves it up to the numerator, okay, which is our seconds there. Let's take a look at a graph of velocity versus time now. We looked at displacement versus time before, but now we're looking at velocity. And here's what I would say. I would start looking at these as little sections. I would say pretty much from 0 to a, we have an increase in velocity. Well, how do you increase your velocity? It means you step on the gas in your car, so you accelerate. So this is a positive acceleration. Then around area B, right here, we have a flat line, which means we have a constant velocity. Well, when are you ever cruising? That's when you have no acceleration. And then finally, after that point, from B onward really, and down this whole slope through C, we notice that in this part of the problem, we have a decrease in the velocity of the object. Which means when there's a decrease in velocity, it means you're slowing down and you're pushing it more in the negative direction, which means acceleration must be negative. Notice at point A, if we look at the slope of the line, it's going upward. and we could look at the point of the slope exactly at point A. Okay, we can say the slope of that line at point A is positive. Well, the slope of the line is positive, and so is the acceleration. Well, let's take a look at point B. At point B, the slope of the line is 0, and the acceleration is 0. And at point C, the slope of this line, if I were to draw it, okay, the slope of the line at point C is negative slope, and is negative acceleration. So what we can say, to generalize here, is something very similar to the other graphs. We could say, in velocity versus time graphs, the slope of the line or the curve is the acceleration. Alright, let's take a look at this table. Let's look at some examples or conditions. Let's say we had here positive, negative, positive, negative. This next one will put negative or positive, 0 and 0. We want to talk about what would happen, what we would need as an acceleration. So let's say in the first case, you're moving with some positive velocity to the right, and you want to speed up. For you to speed up, that means your acceleration needs to be in the same direction as your velocity to push you along, to help you out. So if you're going to the right and you want to get faster, the acceleration has to also push you to the right, so acceleration here would be positive. Now, if you're going to the left and you want to speed up, it means you want to get faster, but faster going to the left. Again, velocity that's negative just means that you're going to the left. And if you want to speed up, meaning go faster to the left, it means the acceleration needs to push you further to the left. So it turns out that the acceleration would be negative here. That would speed you up. Let's take a look at the next part. Say you're going to the right and you want to slow down. You'll notice that to slow down, the acceleration has to act against you, which is a negative, because you're going to the right. But if you're already going to the left, like in this case, and you want to slow down, it needs to push you to the right. Well, how does something push you to the right? It means it pushes acceleration to the right. So what you'll really notice here is this. To speed up in motion, the velocity and acceleration have to have the same signs. But to slow down in your motion in general, it's when the velocity and acceleration have opposite signs. How do you move at a constant velocity? Well, that means that your velocity isn't changing. So that means that you can't have acceleration. So that would be 0. Doesn't matter whether you start negative or positive. But to move consistently or steadily at a constant velocity, acceleration must be 0. To speed up from rest simply means that you need to get faster, starting at no velocity. Well, it doesn't matter. If you have any acceleration at all, negative or positive, you're going to speed up. Whether you speed up to the left or the right doesn't really matter here. And finally, at the end here, how do you remain at rest? If you're starting at rest, you have to have no acceleration and no velocity. That means you have no motion. For the kinematic equations, we're just going to go over the three that exist here. So the first one is just a manipulation of this formula here. If you take this formula and rearrange it and solve for VF, that's what you get there. So that's all that portion is again. Okay, again, a manipulation. So the first equation will be used when we're looking for maybe final velocity, and we have these three, or if we're looking for maybe acceleration, we have these three. But notice the first equation does not have x in it. So this equation has no displacement involved, if you want to write a note. Not using displacement here. The second equation, notice, does have displacement involved in it. It absolutely does. And it has our time and our initial velocity, but it doesn't have final velocity. So this one has no displacement. This one is not used if you're missing the final velocity. And the last one, you'll notice that it's a combination of the first two actually, and it gets rid of time. Right? There's no time in that equation. So if you have every variable but displacement, or if you have almost every variable but displacement and you want to solve for something unknown, you may use this formula. If you know nothing about VF and it's not involved in the problem, you might use this one. If T is not involved anywhere in the problem, you would use this one. But remember that just because you're using X doesn't mean you have to use this problem. If you're trying to find X, but you don't know time, you can't use this here. Maybe you use this one and solve for X and rearrange it, because you don't have time. But these are the three kinematic equations that we're going to use this year to represent motion of an object. Alright, let's take a look at the first example here and decide which of those three kinematic equations we may use. So a race car reaches a speed of 42 meters per second. It then begins a uniform negative acceleration using its parachute and braking system. It comes to rest, keyword comes to rest, in a time period of 5.5 seconds. Find the distance the car traveled during braking. So, let's take a look. It says it reaches a speed of 42, but then comes to rest. So the final velocity is 0 because it comes to rest. Be careful. You might want to think of final velocity as 42 because it says it reaches a speed. Okay, but in this case, it started somewhere else. We don't care where it started. So it reached the speed of 42, then began to brake. So the beginning of the problem is right here. As soon as it reached 42, that's the beginning of the problem. So that's the VI in this problem. Why am I using VI and not speed? Well, because take a look. It's traveling in one direction. It begins a uniform negative acceleration, and it comes to rest. So we know that the acceleration is slowing down the motion. Okay, because it comes to rest, it's acting in the opposite direction. So the time period in this problem is 5.5 seconds. And we want to find the distance traveled, which happens to be the same as the displacement in this problem. But you'll notice we have no way to solve for x right away, simply because the equations that involve x also involve the acceleration. We don't have acceleration. So let's start by finding acceleration. Acceleration is Vf minus Vi, both in meters per second, all over time period. So we really just have negative 42 over the time period of 5.5 seconds. Well, in this problem, it's got to be a negative answer for acceleration, obviously. Well, acceleration turns out to be just negative 7.63 repeating. That's our acceleration we're going to use. So we utilize this formula here, and now we really don't need it anymore once we got the acceleration. So now, given these four variables, let's go ahead and use our new formula. Let's use x equals VIT plus 1/2 AT squared, noticing that we don't need VF anymore because this formula doesn't involve VF. We could have used the third kinematic equation to find x, which does involve VF, but this one is already solved for x, which is what we're looking for. So make it easy on yourself. So I'm just plugging in. Right now, key things to note before we go any further. 5.5 is being squared. Square it first, please. Okay, square it first. The quantity on the left-hand side is going to be 231. And now this is going to be actually minus because of this negative that's going on here. This is like a negative portion. Will turn out to be 115.4. Again, using the rounded value of negative 7.63. Now, this is the reason I went over this, or I want to do this. We could look just at the answer here and say, yeah, sure. It's simply just going to give us 115.5. Now, the one thing to note, though, and this is what we're going to really look at, the interest in, is the following. Imagine this problem there had been no deceleration, and the car had just been traveling at a velocity of 42 meters per second, and it maintained it for 5.5 seconds. Well, if there was no acceleration, nothing slowing down the car, no braking system, this part wouldn't exist. This would be 0. So this whole thing would drop off, and you'd be left with just this portion right here, which is 231. So this is how far the car would go at 42 meters per second for 5.5 seconds. But because it was slowing down the whole time in those 5.5 seconds, this is like a negative distance, okay, or a negative displacement, really. In this case, it's canceling out part of the distance that would have been traveled had there been no acceleration. So with the acceleration in this problem, it only went about half as far as it would have. Let's make sure we write our units of meters here. Example 3 says a plane starting at rest at one end of a runway undergoes a uniform acceleration of 4.8 meters per second squared for 15 seconds before takeoff. What is its speed of takeoff? How long must the runway be for the plane to be able to actually take off? So, we've got starting at rest. Then we've got an acceleration of, and finally we've got a time period of. And this problem is asking us, what is its speed at takeoff? What is its speed at takeoff? So this is the beginning here when it starts at rest, and as it's taking off, that's the end of the problem. So find that. And how long must the runway be? Really means how much ground does this plane need to cover to actually take off. So we're looking for the displacement. So in this problem, it's actually quite simple. We've got these first three pieces of information here. We want to find VF, start with VI plus AT. Well, VF is going to be 0 plus 4.8 meters per second squared times 15 seconds. It's going to give me a final velocity in this problem of 72 meters per second. Now, knowing the final velocity, we could solve for x, the displacement, in different ways. We can go to the third formula now that we know VF, but the third formula is not solved for x, so let's stick with the second formula again. Let's continue to work with the second formula here. Plugging in what we know, this is 0, it drops off. Remember, again, to reiterate, square this first, then multiply it by these two quantities. Make sure you PEMDAS it. Square it first. What you're going to end up getting for this portion of the equation is 540 meters. So if you were writing a verbal statement on your test, you would say the speed of the plane at takeoff is 72 meters per second, and the length of the runway must be at least 540 meters for it to actually successfully take off. Where is an application of this? Please, right away, think about aircraft carriers. Planes need to take off all the time from ships, and they only have a certain amount of runway. If they don't successfully, they could, launch off into the water. The final example says a person pushes a stroller from a velocity of 3 meters per second, looks like starting velocity, uniformly accelerating it at a certain rate, acceleration. What is the velocity of the stroller after it has traveled a certain length? So we know initial velocity is 3 meters per second. We know acceleration is a half of a meter per second squared. We also know that it's traveling a certain distance. Well, in this case, since acceleration and velocity are acting in the same direction, we can tell us that 4.75 is actually the displacement. And we're looking for VF. So we know this formula is usable. We know it's usable because we know everything on the right-hand side of the equation here. Okay, again, we know everything on the right-hand side of the equation. Let's go ahead and plug into what we know. Now, plugging in all these quantities, we're going to end up getting the following. Now be careful because your units here are meters squared per second squared. Because again, you squared your units here. This meter and this meter made meters squared over second squared here. Well, the reason you still have squared units is because you have to take the square root at the end. So your final velocity, you get the square root of this whole thing. Remember, it's plus or minus always. Now, it's plus or minus 3.71 meters per second. Well, take a look. It says that the starting velocity was 3, and it accelerated with a positive velocity, so it's got to get faster than 3. So in this case, we have to use the positive root because of that. So again, you'd have the positive root for this one because it's accelerating it, and it's already started at a positive velocity. Your homework in this section is from 3 different pages.